Hi everyone, I am Aryan from University of Minnesota, and today I am going to talk about our paper Sample Efficient Bayesian Optimization with Transfer Learning for Heterogeneous Search Spaces. This is joint work with Sait, Yuhou and David from Meta. So Bayesian optimization is a very well-known and effective framework for black box optimization. And in the last decade or so, we have seen so many real-world applications of BO, for example, in AUTOML, materials design, and drug discovery. Commonly in settings with budget of very few function evaluations, successful application of BO often requires transferring information from historical experiments, and there is a lot of work on transfer learning for Bayesian optimization, but all of these traditional approaches typically assume that all the related experiments have exactly the same search space. However, in many real-world settings, the search space often vary across related tasks. For instance, when tuning hyperparameters of machine learning models, practitioners often make changes to the search space by adding or removing parameters. One example of that shown here. And this is the challenge we look to address in this paper. Concretely, our objective is to optimize a target black box function ft with a limited evaluation budget. And we are given data from T-1 related optimization experiments, which we refer as source tasks. And our goal is to leverage this existing data to improve the sample efficiency of BO on the target task. And the key challenge lies in the heterogeneity of search space across these tasks. We propose two methods to address this challenge, and I'll go over them one by one. And we'll focus on kernels over inputs or the parameter space today, but in transfer learning, we usually combine this kernel over inputs with a task kernel that represents the task correlations, and hence the name multitask GP in both the methods. In the first method, we define a conditional kernel for heterogeneous search spaces. So the key idea behind conditional kernel is to first construct a tree structure representation of all the search spaces, and then leverage a set of base kernels, so this could be something like a matern kernel, to conditionally compare inputs from different tasks based on their matching parameters in this tree. And let's look at an example to understand this kernel more. So let's look at this example of hyperparameter optimization where we have a target task F3 and we have two source tasks F1 and F2 and their parameters or input space is listed here. So this is how the dependency tree looked like for these search spaces. So what we did was we start from the root node and we assign a maximal subset of parameters to each node that are common across as many tasks as possible. And each node also gets its own base kernel denoted by K1, K2, K3 here. So now given this tree, we can compute the conditional kernel. So for example, for any two inputs x and x prime coming from task I and I prime, the conditional kernel is going to be defined as the sum of base kernels over all nodes that contain the common parameters across both task I and I prime. As an example, let's say one of our input is coming from task 1 and the other is coming from task 2. Then you can see the common parameters for these two tasks is the root node parameter. So the kernel is just the base kernel at the root node, which is K1. If the inputs are coming from task 2, if both the inputs are coming from task 2, then the common parameters is this left path. So that's why the conditional kernel is the sum of two base kernels K1 and K2. In the second method, we study this approach that treats each missing parameter in any task as an additional hyperparameter in the MTGP model. And then these missing parameters can either be learned jointly with other GP hyperparameters like length scale or set to some expert chosen fixed value. And this is motivated from hyperparameter tuning applications where missing parameters represents settings that have not been tuned in the experiment. We evaluate both the methods on both synthetic and hyperparameter tuning benchmarks. Here is one representative result on hyperparameter tuning. And as you can see, the MTGP with conditional kernel performs better when we have small number of source trials. And as the source data increases, the learned imputed MTGP method, the second method, performs better. Please see other results including baseline descriptions in the main paper. Thank you very much for listening.